Hi, I'm Barbara Fox, and today I'm going to talk about IP routing and how and why it evolved to MPLS, and then how MPLS has evolved over time, what issues were being addressed, and how we're evolving to segment routing and with Path Computation Engines or PCEs. So let's start with the way layer 0, 1, and 2 networks set up their connections. For the most part, they use connection-oriented protocols. So they set up connections between the two nodes and forward traffic, between two nodes and forward traffic. And these are considered hard connections, meaning that the state is stored in the network and the connection stays up until it's brought down. The elements themselves are usually pretty hardened because they have to keep the connections up until they're brought down. And then the devices usually have redundant elements in them. They keep track of state, like which resources are being used and what's available for use. So layer 3 routing takes a different approach. Traffic is sent in a connectionless manner. So each packet is forwarded hop by hop across the network. So this means that the network does not have to hold the state of the connections, nor does it really have to track its resources. It receives a packet, it figures out where it needs to go next, and it forwards it on. And if an NE dies, the network just routes around it. So with IP routing, each node has a loopback address that identifies that node. And OSPF and ISIS are the interior gateway protocols, the IGPs, that share routing information between nodes. So in this diagram, node 6 would advertise that it had connectivity to 10.10.30/24. And node 7 would advertise that it had connectivity to 10.10.31.0/24 and 10.10.30.200 with a /29, which is actually a subset of this node up here. So OSPF and ISIS are link state protocols. So that information is advertised to all of the nodes in the network. And because they're link state protocols, every node in the network has the same complete picture of the network, so that nodes compute the same least cost path from any node to any other node in the network. And that's important, right? Because you don't want to create loops in the network. So every node knows the shortest path from every other node to the destination. So in this diagram, say we were going to inject a packet from 10.10.31.100, and we want it at node 5, and we want to send it across the network. What happens is that every node will do a longest match. So the routes that were learned are stored in the routing database, and they're in the forwarding database, and they're stored with a mask, and the longest match, and we'll do longest match first. So in this case, we have a 10.10.31.100 as the destination. We will AND it with a /29, and if the result is 10.10.30.200, then we would forward it. But in this case, it's not. And then, so the next thing we'll do is we'll mask 10.10.31.100 with a /24, but we don't get this, so we don't forward it. So we check it against the next entry. So we mask this with a /24, and we do get 10.10.31.0. So we forward it out this port to 10.10.0.18, our next hop. So now the packet has arrived at node 3. So node 3 does the same thing. It checks it against its first entry, its second entry, its third entry. It matches. So it forwards it to 10.10.0.22. So it forwards it out this link. Now this node does the same thing. It checks it against its routing table, its forwarding table, sees a /24, sends it to 10.10.0.26. And then at this node, he forwards it based on his routing table to the correct node. So as more and more, so this is a lot of, everybody's checking their routes. So as more and more traffic is pushed on the internet, it seemed like a bad idea to be doing hop-by-hop routing for every packet at every router in the core of the network. So it was putting a lot of pressure on the core routers. So there was this company called Ipsilon in the 90s that started doing IP and IP. So what they would do is they would know that the destination node was node 7, so they would encapsulate the IP packet in an IP packet that was destined to 10.10.127.7, and then that outer IP packet would be stripped and the packet would be forwarded. So this was, a brilliant idea. And if everyone did this, the core nodes would only have to route to the other nodes in the network. They wouldn't have to route to every IP destination. So that would significantly cut down on the number of destination IP addresses the core routers needed to route. So LDP was invented, the Label Distribution Protocol. So now the IGPs would advertise a local label with the routes that it was advertising. So in this case, 10.10.127.6, node 6 would advertise the route 10.10.30 with a /24 and say, use label 333 on this link to get to that network. And node 7 down here would advertise both of these networks and say, use label 633 to get to me to get to those destination addresses. And then node 2 would say, okay, if you want to get to 10.10.31/24 or 10.10.3200/29, use label 482 to get to me, and then I'll forward it on. And then node 3 would say, if you want to get to any of those networks, use label 137 to get to them. And so every node was advertising a local label to it to get to those particular routes. So the traffic is unidirectional, right? Because basically it's telling you if you want to get to this destination, say we still wanted to get to 10.10.31.100, these labels would tell us how to get there. The cool thing about this is only the LERs, the label edge routers, actually had to look into their routing table. And when they looked into their routing table, they would find a label that they should use to forward the traffic. So this is pretty cool, right? So in this case, we're going to 10.10.31.100 again. He looks it up and he says, oh, that goes out this port with label 137. He gets to label 137. And now this node looks and says, oh, my in label 137, that has an out label on this port of 482. So it sends it out 482. 482 receives it and says, oh, in label 482, goes out label 633. Every node is using the label, except for the egress nodes. Every core node, every transit node is using the label to figure out where it goes next. And the labels are a fixed size. So it's a much easier lookup. So this is cool, right? But connections weren't end-to-end. So if node 3 also had a packet for 10.10.31.100, it would also send it out 482. And if node 2 had another packet that was going to 10.10.31.99, it would also send it out label on 633. So as the traffic got closer to the nodes, the pipes were using more bandwidth, right? There was more packets in the label as it got closer to the node. But this is exactly the way that routing works. So that wasn't really a big deal. So connections aren't end-to-end, and the pipes are getting fuller the closer you get to the nodes. So as it turns out, the service providers wanted to be able to engineer their IP networks in the same way that circuit networks are engineered. They wanted to be able to make use of little used lines, and they wanted to be able to upsell connectivity with particular constraints like bandwidth, jitter, affinities, or SRLGs. So at that point, RSVP-TE was invented. So with RSVP-TE, the IGPs assigned characteristics to the links like bandwidth, colors, affinities, SRLGs, and those characteristics were distributed with the IGP flooding. So that information is kept in a traffic engineering database. So the head end or the source determines the route, determines the entire path, right? And what it does is it looks at all the links that are in its TE database, and it discards any links that don't meet the criteria of the connection that it's going to set up. And then it runs the Dijkstra on the remaining links. So at that point, it knows the path, and that's called a constraint-based open shortest path first. So the head end knows what the path to the egress should be, and it creates an ERO, an explicit route object, an ERO, that defines the path. And that path can be strict or it can be loose. In strict, every link along the path is determined, or loose, you can say, I just want to traverse these particular links. So the ingress node sends a path message along the path describing the connection that needs to be made. And so the path message goes to the destination, and then the labels are allocated on the way back with the RSV message. And now you have an end-to-end connection from the source to the destination. And it meets the criteria that was requested. It's still a unidirectional tunnel. You're still sending the traffic from node 5 to node 7, but it is an end-to-end path with specific characteristics. So now the transit nodes have a little more state that they need to keep. So say we requested 1 gig of bandwidth for this connection. Every transit node needs to know that its link now has 1 gig less of bandwidth available for other paths that are going to be made in the network. And so now it starts flooding that it has one less gig of bandwidth when it does its IGP flooding information. So this means that these transit nodes, or label switching routers, LSRs, they're going to perform a CAC function, right? If they know how much bandwidth they have available and they're flooding that information, they basically know that they're allocating this much bandwidth for a particular connection. And so there's soft state that they have to keep. They have to know that a certain amount of bandwidth is allocated for this particular connection. And then they're going to get periodic refreshes on that tunnel that says, I'm still using the bandwidth, I'm still using the bandwidth, I'm still using the bandwidth. And if they don't get those refreshes for a certain amount of time, they'll release the bandwidth so that it's available for other connections. So people really complained about these soft state messages. Maybe they were a bigger deal when the transit links were smaller, but more bandwidth covers a lot of ills. So the other issue with soft state is that the head end doesn't necessarily know that if there's a problem in the network and the connection's gone down. So BFD was invented. And BFD acts a lot like CCMs at layer 2. So basically what happens is that you send end-to-end information saying that you're alive, and it's returned back. And if 3 of them are missed, then the endpoints know that there's a problem with the connection and the network. So when there's a problem, how do you fix it? Do you fail all the way back to the head end and resignal the entire route for RSVP, or do you wait for the network to converge for LDP? So next, FRR was invented. The network operators wanted something faster, right? They didn't want to wait for the connection to be resignaled. I mean, it's a scaling nightmare. And they wanted to be able to, they were used to circuits failing over in 50 milliseconds. So they wanted to be able to have something that was really fast. So they invented fast reroute. So for fast reroute, there's 2 modes. There's link and link node. So in the case of a link, what happens is that the fast reroute determines that if this link goes down, I'm going to tunnel the traffic that would have gone over this link, and I'm going to put it on another path. But so if the traffic would have gone on this link with a label of 482, a new path is created to bypass that link. And the packet still has the 482 in it, but there's also a bypass label so that it can bypass this link, arrive at the destination node with the same label. When the 115 in this case is popped off, now the node is able to look up 482 and know that it's going to forward the traffic out this link with 633. So that's called next hop. There also is node link, which is next next hop. So instead of bypassing the link, what you do is you bypass the node. And so you want to go to that node's next hop. So you're going to the next hop. So in this case, this is a little bit not quite perfect, but in this case, if the label was going to be 633 that got forwarded here, so we would bypass the tunnel. Now the problem with this is that actually this is the penultimate hop, so it wouldn't actually put the 633 in on it. So I'm not carrying the extra label here. I'm just forwarding the traffic around this node to arrive here to be forwarded out. But if we just talked about it in the way, if this wasn't a penultimate hop, then we would include 633, and we would put a bypass tunnel of it that went 114, 116, 115. And when it got here, it would pop the 115. It would have the 633, and it would forward it to the next hop. So this helps everything recover much more quickly. The nodes realize, these nodes know there's an issue immediately, so they know that to invoke the bypass that they're using at this place. And if the failure continues, RSVP tunnel can be reestablished with a make before break. So if this tunnel doesn't come back and it turns out that the network needs to be, rebalanced, node 5 can create a new RSVP tunnel and then switch the traffic to it and then break the old one. And LDP will reconverge also for a better route. Okay, so this brings us to MPLS-TP. So MPLS-TP is like a circuit in that the connection is bidirectional and associated. With RSVP-TE, it was unidirectional, and if you were sending connections between two tunnels, you had to create one at either side. With MPLS-TP, it's bidirectional and associated. So TP is signaled with GMPLS, which is a generic protocol that can be used on non-IP network and can carry non-IP traffic. So like the optical guys like this. LSPs are set up between the loopback addresses on the ingress and the egress nodes. And MPLS-TP is similar to RSVP-TE in that the connections support TE capabilities. As with RSVP-TE, the CSPF algorithm is used to determine the path. So any links that don't meet the criteria are thrown out, and the best path is algorithmically determined at the source route. The other difference is that the labels are included in the path packets as well as the RSV packets to set up the connection in both directions. So when the path connection goes, he will send the label along with the requirements for this connection to the destination node, and then the RSV reply will set up the labels in the return direction. And the other difference with MPLS-TP is that you can set up a primary tunnel and a backup tunnel. Then you run BFD over the LSP, and if you fail, there's a backup tunnel that you fail over to when you miss 3 BFD packets. So MPLS-TP solves many of the problems that RSVP-TE solves. It's just that it's dynamic and co-routed. Before we move on to segment routing and Path Computation Engine, let's talk about pseudo wires. So tunnels connect routers together, and then the pseudo wires can connect the customer ports together over the tunnels, and they can be created dynamically using targeted LDP. So if we wanted to make a connection from A to Z, it could run over an RSVP-TE tunnel, or could go with LDP, could go with over an MPLS-TP tunnel, but it would have a label and it would ride over that tunnel. And then that is the pseudo wire that would be connected. So let's talk about segment routing. So at first glance, segment routing is a lot like topology LDP. The routes are advertised with a prefix, SID, that identifies the node on which the route can be found. instead of just a label. So unlike LDP labels, the prefix SIDs are globally unique in the network. So the same SID will be identified with the same egress node by all the nodes in the network. So I'm going to gloss over some of the details, but basically to get to the egress node 10.10.127.7 in this diagram, every node in the network forwards that node to that node with a SID of 7. So if any node is trying to get to 10.10.127.7, it forwards with a SID of 7. And so it works like LDP. It's still shortest path towards every destination, but every node uses the same SID to get there. So this SID is globally unique. Okay. So we still have the same traffic engineering problems that we had with LDP. If we want to make better use of the network, we need to be able to choose particular routes that maximize the network's resources. So we need to be able to traffic engineer our tunnels. So in addition to the prefix SIDs, we have adjacency SIDs. And adjacency SIDs are assigned to individual links on the nodes, and they are locally significant. They allow you to steer the packet to a new segment through a particular link. So in the way that the IGPs advertise labels with routes, now they advertise a SID to the whole network that understands the globally unique identifiers. So in this diagram, we're forwarding the packet to 10.10.31.100. And if we want to forward using the shortest path, we just put a SID of 7 on it and we forward it along the path, and it just takes the shortest path to get to node 7 to be forwarded on. But say we don't want to follow the shortest path. For some reason, we want to forward the traffic through node 1 and node 6. So if we just put 7 as the label, we would follow the shortest path. So we don't want to do that. So what we're going to do, the first SID that we'll put on it is 1, right? Because we want to get to node 1. That's the first hop that we want to get to. So our outer SID will be SID 1. Now say that the shortest path from 1 to 7 actually traversed node 2, and everybody in the network knows that because we're all running the same algorithm with the same database. But we want this path to traverse node 6. So we use an adjacency SID of 16.006 to get to node 6. So that would be the second SID that we put on this packet. And then now we want to go from node 6 to node 7. We can follow the shortest path, so we can just put the SID of 7 on it. So we took our packet that had a destination IP address of 10.10.31.100. We added a SID 7 for the last hop, SID 16.006 for the link, and then SID 1 for the first hop. So we followed the packet. So this is different from RSVP in another interesting way. The network nodes themselves don't know anything about the tunnel. They don't know it exists. So they're not tracking it. There's no soft state in the network. So remember that in RSVP-TE, the routers would allocate an amount of bandwidth to a particular tunnel that was traversing it. These nodes are completely unaware of the tunnel. There's no soft state. And this information is going on every single packet that's being forwarded. That route is being put into every packet that's being forwarded. So this is really software-defined networking, right? The information, the nodes themselves don't really know anything. The node's just forwarding. They're just doing what they're told. And now we have the potential for MPLS functionality without the complexity of all the protocols and the state and the network elements. So this is like clean IP. It's just doing what has to get done. But that's why the Path Computation Engine is so important, because the network itself isn't holding and monitoring state. The software controllers and the orchestrators need to have that information. So this is why the Path Computation Engine is so important, because the nodes themselves aren't holding any state. They're not monitoring the state of the network. So the software controllers and the orchestrators need to have that information. And the Path Computation Engine needs to understand the topology of the network, the state of the network, and the throughput being used on each link. And it uses this information to create a source route that each packet will embed to its destination. So how does that work, right? So the PCE peers with the routers in the IGP. So it doesn't advertise, it acts like any of these nodes, except that it doesn't advertise any routes and it doesn't advertise any labels. It's not a destination for anything, but it has to have the same routing database that all the other nodes have so that it can make the right decisions. And so when all these nodes advertise their links and their routes and stuff, the PCE learns it as well. And when there's a fault in the network, the controller learns that through the IGP as well. So the PCE runs computes based on the policies required by the service and the tunnel, and it does that in real time based on the state of the network. So what's important about a PCE? So, there's a lot of information in the network, right? There's a lot of things that you need to know. There may still be RSVP-TE tunnels and LDP and all that going on in the network. And maybe not all of the nodes in the network are going to run segment routing. And so the Path Computation Engine needs to understand what's going on in the network, and it needs to learn it. It needs to be able to talk to all of the nodes and learn what they're doing, what their state is, and what they're doing at the time. So it'll be interesting. It'll be interesting to see how the network evolves from here. What's the next problem that we're going to have to solve, and who's actually going to be able to take advantage of segment routing and who isn't. So that's the overview. I hope you got something out of it. Thank you.